Hey guys, welcome back. So today we're going to do one of the main topics of calculus, but we're going to do it from a very casual approach, and then we'll get a bit more serious with it tomorrow. Okay? So average versus instantaneous velocity. If I were to give you a graph that looked like this, I want you to just look at it for a minute and figure out what it represents. So if this is a graph of a 2-hour trip, a distance of 100 miles, okay, then what's going on at the different parts of this graph? For example, maybe what's happening where the graph is steeper? How would you put that in words? So at this spot right here where the graph is a little steeper, we're covering more distance in less time. So if we're covering more distance over less time, that means that's a spot where you're going faster. Just common sense. Okay, well, how about a spot where it's kind of flattened a little bit? Almost flattened out right here, but not quite flattened out. What would that represent? If it were flat, then you are taking up more time with less distance. If you're covering more time in less distance, if time goes on but your distance doesn't, you would be stopped. Since that's not completely flat, you're going really slow. You're in traffic. So just to summarize, just a little common sense, if this is distance over time, then at the beginning of my trip, I kind of speed up, get a little faster, slow down, traffic, almost stopped, and then I'm speeding up again. The whole trip took 2 hours, and it was almost 100 miles. Looks like more like 90 miles there. All right, well, here's another scenario. Let's say you take a 200-mile trip. You go on a trip for 200 miles, and it takes you 4 hours. Just off the top of your head, what can you summarize? Anything. What could you come up with? You drove 200 miles. It took you 4 hours. If you drove 200 miles and it took you 4 hours, well, that's 50. And if I look at the units, it's 50 miles per hour. But what is that? What did you just find? Is that how fast you were going? At every moment, at every time? Were you going 50 the entire trip? Hopefully you're saying no. What you found is your average speed. You're averaging a speed of 50 miles per hour for the entire trip. Does that mean you were going 50 the whole time? No. You might have been going faster, you might have been going slower, you might have been stopped, but you were going 50 on average. So formally, your average speed, your average velocity, there is a slight difference, we'll talk about that later. Your average speed is 50 miles per hour. And to find average speed, it's your total distance divided by your total time. Total distance, think miles divided by total time, hours, miles per hour. That makes sense for speed. That's why the units are so helpful. Miles per hour, total distance divided by total time. And if you think miles per hour, it tells you what you should be doing. Now, this may not make so much sense yet. Graphically, that would be the slope of the secant. You might not quite get that yet, but we'll come back to it. It's going to be a big concept in calculus. Okay, you can write it down for now, and I'll explain in a minute. The slope of the secant is going to be your average rate of change. So if we go back to this trip that we started with, if I wanted my average speed for the entire trip, then it would be, I went 90, I think that's 90, 50, 60, 70, I went 90 miles in 2 hours. So my average speed for this trip would have been 45 miles per hour. Okay, there's the bell. Well, graphically, that's the same as the slope of the secant. And what that means is you connect the endpoints, the beginning of my trip to the end of my trip, connect that with a straight line. Wish me luck on this. Hey, not bad, not bad. Pretend it was straight. And that slope, the slope of that secant would be 45 miles per hour. Why? Slope is rise over run. From the beginning, I would go up 90 and over 2. 90 over 2. So when they say average speed, it's the slope of the secant. Now this is going to have more applications than just speed. It's going to be any average rate of change, okay? Now again, what does it really mean? It means it's my average for the entire 2-hour trip. Does that mean I was going 45 miles per hour the entire time? No, I was definitely going faster than that right here where the slope is steeper. And I was definitely going slower than that here where the slope is not as steep. So that should bring us to, well then how do I find out the actual speed at any given time? The average rate of change is my average for the whole trip. But how do I figure out how fast I was really going at every moment along my trip? How fast was I going here? How fast am I going here? How fast am I going here? Well, that's going to be the slope at each of those points. Well, the slope right here, we call that the slope of the tangent line. If the curve is straight, then it looks like it's the same as the curve. But if it's not, you have to draw a tangent, a line that just, let's say we want the tangent right here at this spot right here. I would have to draw a line that just touches that one spot. That would be the tangent. And this would tell me the speed. The slope of that tangent would represent the speed at just that spot at 1.5 hours. I'm getting a little ahead of my PowerPoint, so let me go back to where we were, and I'm going to say all that again. So if you didn't quite get it, it's okay. Right now, we pretty much just have the average rate of change. Okay, so right now the average speed we discussed is the slope of the secant, which is the slope connecting the endpoints, the beginning and the end of whatever the scenario is. The instantaneous speed, the speed you're actually going at that time, that would be the speed that your speedometer shows in your car, and graphically, that's going to be the slope of the tangent. Okay, now let me show you how you do that again. This is the same trip. This is the same trip that we were talking about before. Okay, but read the question very carefully. Make sure you pay attention to whether it says average velocity or instantaneous velocity. Average velocity will be slope of secant using endpoints. Instantaneous velocity is slope of tangent. All right, let me show you what that means. The average velocity in the second hour of the trip. Well, anytime they say average velocity, you need a beginning and an end. Since it's a second hour of the trip, the beginning would be here, the end would be here. Okay? They want the average velocity for the second hour of the trip. Graphically, that would be the slope of the secant. Okay? You can either count squares and do rise over run to get from here to here and answer that question, or write down the coordinates and basically do your Algebra 1 slope formula. Subtract the y's, subtract the x's, or remember, it's speed. It's change in distance over change in time. So the coordinates of this point at the end would be 2, 90, and my starting point is 1, 50. So the average speed would be 90 minus 50, or 40 miles, and it took me 1 hour. So my average speed for the second hour of the trip is 40 miles per hour. Okay, so that was the average speed in the second hour of the trip. But remember, that doesn't represent how fast you were going at every given moment. If I want to know how fast I'm going at each individual moment, I have to use the slope of the tangent. Let me now focus on that. Okay, this next question is asking, what is the instantaneous velocity? at t of 1. Okay? Well, there's a hint, by the way. If I want to know instantaneous velocity, it's at a single moment. If I want to know average velocity, I need a beginning and an end. That's a hint. You'll need 2 times to work with. All right, so instantaneous velocity at 1. I go to 1, and I'm trying to figure out what is the slope right here. What is the slope of this little piece of the curve right there compared to the slope of my average? Well, it looks like it's not quite as steep as the average was. So I'd say it's slower than what we just calculated. But how do I figure that out? To find the instantaneous velocity at 1, you start by putting a point on that point in question. Okay, put a point right there if you can. And then you use a straight edge to try to draw a tangent that touches that point perfectly. Let me see what I can do here with this thing. That's a little bit off. I do my best. Use a straight edge, though. You kind of want the same amount of space over here as you do over here. The tangent has to touch that curve in just that one spot. Now, I know I put it in the computer, so I kind of did it with the computer. So let me catch up for a minute here. There's the best I could do. But the tangent is just supposed to touch the curve in one spot. Now, to estimate the instantaneous velocity, you need the slope of that tangent. Okay? So, slope of secant, let me start over. The average speed requires you to have endpoints, and you find the slope of that. The instantaneous speed requires just 1 point, and you find the slope of the tangent. Draw a tangent by hand, and now you have to estimate the slope of that tangent. That means your answers aren't going to be exact. That means you cannot expect your answer when you check the back of the book to be exactly right. So right now we are estimating the instantaneous velocity at 1, and don't expect yours to be exactly the same as mine. So we're going to try to get the slope of this tangent right here. To calculate the slope of that tangent, I find any 2 points on that tangent. I'm going to use definitely the point of tangency as 1 point. The other point can be any point along that tangent. It doesn't matter which one. If there's one that's convenient to read, then use that. So I'm going to go with this guy right here. Okay? To answer this question, the instantaneous velocity at 1, I need to find the slope using those 2 points. So the coordinates of the second point would be 1.5, comma, and see, this is even an estimate. It's not quite 60. It's not really 55. Maybe I'd call it 56. Clearly, this is an estimate. The slope or the coordinates at 1 would be 1, comma, 40. So the approximate instantaneous velocity at 1 would be the change in distance divided by the change in time. So this is miles per hour. So 56 minus 40 would be 16 miles. 1.5 minus 1 would be 0.5 hours. And 16 divided by 0.5, or 16 divided by 1/2, is the same as 16 times 2. So that's 32 miles per hour. So compare that. It looks, remember, what did we get for the average rate of change earlier in this problem? We said that was 45 miles per hour, I believe. And this looks like it's not as steep, and we just estimated it to be 32 miles per hour. It seems reasonable, at least. Now, what do you need to get from all of this? Okay, here it is in a nutshell. If I say average speed or average velocity, you need 2 points, the beginning and the end, and its slope of secant. If I say instantaneous velocity at a specific point, you use just that 1 point, use a straight edge, draw in a tangent, and then find 2 points on that tangent. But for all of it, it's basically your algebra 1 slope, change in y over change in x, or total distance over total time. And here's a summary of all of that. This, you do need to put this in your notes and make sure you understand it. Okay, now technically velocity and speed are not quite the same. They just sort of were for that last example. Velocity, the difference, those of you who have had physics or maybe, I don't know, maybe even sooner in science, velocity and speed, velocity also gives direction. Speed is the absolute value of velocity. So if you get a positive velocity, it means you're going forward or up, depending on the scenario. When you get a negative velocity, it means you're going backwards or down. It doesn't really matter yet in this lesson. Okay, so average velocity requires 2 points. Instantaneous velocity requires just 1. Now we're going to apply that to a couple more problems. Okay, in this problem, the most important thing to do is make sure you understand what your variables represent. Okay, t is time, duh, but what is this f of t? Okay, f of t is a height. So what would the units be? Well, if it's height, we can see here, our units are feet. Okay, so if I want velocity, average velocity, remember, is slope of secant using 2 points, okay? But velocity, if we just focus on the units, velocity is a speed, so it would be feet per second. And that kind of gives you a hint. You need the total change in distance over total change in time. Well, the change in distance is what you get when you plug in the 1 and the 4 to this equation, because that'll give you the height. So in short, to find the average velocity here, it's going to be f of 4 minus f of 1 all over 4 minus 1. Because the units would then give me the change in feet over the change in time. So you now have to plug the 4 into the equation up here to find the ending height. Plug the 1 in for time up here to find the beginning height. And then find the change in distance over time. Okay, you really have to read carefully and actually think about it. Okay? They want to know how long it takes for the rock to hit the ground, but you really need to know where the rock starts. It's falling off of the cliff, and the cliff is 576 feet high. Then we have this formula that gives the distance in time. Well, it's the distance that it drops. Okay, in t seconds, the rock drops a distance of that much. So if it's on the ground, what is the distance based on the wording of this problem? So in this case, the distance at this point in time, is it 0 because it's on the ground? Hopefully you said no. The distance when it's on the ground is it traveled 576 feet. Okay, so D is 576. So we have 576 feet it traveled, and we want to know how long it took it. So divide by 16 on both sides. When you divide by 16 on both sides, you get t squared is 36, so t is 6. Can't have a negative time. So how long does it take the rock to hit the ground? 6 seconds. Okay? That's the first part of this question, figuring out how long it took it to hit the ground. Now, they're kind of being gentle to you in this question by giving you that. Basically, it took 6 seconds for this problem to end. The rock started at 0 time, 576 feet high, and it ended on the ground 6 seconds later. All right, the next question is kind of common sense, but some people don't have common sense in math. I know I lacked a lot of it, so let's see if you can figure out where this is going. Okay, what is the average speed of the rock? The last question really gives a big hint on that, okay? But the average speed, remember, it's the total distance over total time. Total distance is feet. Total time was in, what is this, seconds? Seconds. Feet per second. Average speed is feet per second. Well, the total distance, it went from a height of 576 to 0. So you could say you're subtracting them, okay? The total time, it would have been what you found in the last problem. So you would have had to do that even though they didn't ask you to. That's why this was a help. So the total time it took to hit the ground was 6 seconds. So the average speed would be what you get when you divide that, 576 divided by 6. And that's 96 feet per second. Now, if they said velocity instead of speed, I would have to pay attention to the negatives here, but they said speed, and speed is always positive. Okay, well, I hope you're doing well. This is just the beginning. If you're having a hard time understanding this, don't worry. We're going to do more of it as the week progresses, and we'll do it in more than one way. So give it your best on your homework. Try not to stress, but don't give up either, okay? I'm going to skip this last question. Good luck. Here's your assignment. Hope you're doing well, people.